Hi, here we discuss about array of two isotropic point sources. We know that what is meant by isotropic radiators. Isotropic radiators means same radiation intensity in all direction. And what is meant by point sources? Point source means we consider infinitesimally small antenna elements. That's why we call it as point sources. We want to study 5 cases. The first case is that we consider 2 point source of same amplitude and phase. That means we apply current in same amplitude and phase. Just check this figure. Here we consider 2 antenna elements. First antenna element is placed here and second one is here, and the distance between antenna element is D. D is the distance between two antenna element. Then we consider a far distant point P. P is the point and the total field at the point P is we want to calculate. Okay, then we consider E0. E0 is the strength of electric field at point P due to either of sources. Then the total field, total electric field at the point P, it is the vector sum of field due to each sources. We consider two sources, and first source is here. Here the first source. This is the first source, and second source is here, and the distance between the source is D. We want to find the electric field at the point P. That is the vector sum of field due to each sources. And if we consider the vector sum, we want to calculate the path difference. We want to calculate the path difference between these 2 point sources. We know that the R1 is the distance from the first source, R2 is the distance from the second source. So we need to find the path difference. For that, we consider a point. This is the point and it is the reference point. This is the origin. So from the origin, there is a distance R to the point P. And the angle is a theta. And if this is the angle theta, here also angle is theta. So this distance, this much distance can be represented as d by 2 cos theta. How can you compute it is a d by 2 cos theta? Because we know that the distance between 2 point sources is d. So this is the origin. This point is the origin. So it is the midway between these 2 point sources. So the distance between origin and the second source, it is a d by 2. The same distance also from the first source to the origin, that is also d by 2. Using Pythagorean theorem, you can compute this distance as d by 2 cos theta. The similar way you can compute this distance also d by 2 cos theta. So total path difference is d by 2 cos theta plus d by 2 cos theta. So you will get d cos theta. That is the total path difference. A phase difference will be erased due to this path difference. Due to this path difference, there is a phase difference and it can be computed by 2 pi by lambda into the path difference. We know that the path difference is d cos theta. So 2 pi by lambda into d cos theta, that is a phase difference due to this path difference. Here we know that we apply the current in same amplitude and phase. So there is no phase difference due to the applied current. Only the phase difference is due to the path difference. So psi, the phase difference psi is only due to the path difference and it is given by 2 pi by lambda into d cos theta. And it can be represented as beta d cos theta, where beta is a phase constant and beta is equal to 2 pi by lambda. Next, we want to find the total field at the point P. It can be computed as vector sum of field due to each sources. So the net electric field, so E is equal to E0 into e raised to minus j psi by 2 plus E0 into e raised to plus j psi by 2. Okay, first we check why we use psi by 2? We studied that psi is the phase difference between point sources. Psi is the phase difference between the point sources, but here we find the electric field with respect to the origin. Here the reference point is origin. With respect to origin, we compute the electric field. Okay, so with respect to origin, what is the phase difference? Psi is the phase difference between two point sources, and the origin is the midway between these two point sources. So the phase difference between a point source and the origin is psi by 2. That's why we use psi by 2 in the equation. Next, we want to check why we use a negative sign and positive sign here. The reason is that here we advance and delay the sources. That's why we use a negative sign and positive sign. So the total electric field equation is that E0 into e raised to minus j psi by 2 plus E0 into e raised to plus j psi by 2. And the psi by 2 is the phase difference at P due to one source when measurement is with respect to origin. Then we can simplify the equation. For that we multiply and divided by 2. So this is in the form of a cosine term. So we can get 2E0 into cos psi by 2. And we know that psi is equal to beta d cos theta. Substitute here. So electric field is equal to 2E0 cos beta d cos theta by 2. Then next we want to find it's a normalized electric field. For that we can use E by its E max. We know that it's a maximum value. Electric field maximum value is 2E0. Why? What is the reason? Because cos theta for a cosine term it have maximum value is 1. Cosine term have maximum value 1. So E max is equal to 2 into E0. So En is equal to E by E max, that is E by 2 into E0. So you will get cos beta d cos theta by 2. Next we want to draw the radiation pattern. For that we want to assume the distance. Here we assume the distance is lambda by 2. This is an assumption, not a general case. Here we assume a distance that is equal to lambda by 2. In your question paper you must take care what is the distance d is given. If it is a lambda by 4, substitute lambda by 4. If it is lambda by 16, substitute lambda by 16. Here we assume that let d be lambda by 2. So substitute lambda by 2 here. So you will get En is equal to cos 2 pi by lambda into lambda by 2 cos theta by 2. You will get cos pi by 2 cos theta. We can plot its radiation pattern. For that we want to find its maxima, its minima, that is a null and half power points. First we can find its maxima. At maxima means it is a cosine term. So maximum value is plus or minus 1. So En is equal to plus or minus 1, that is a maximum value. So cos pi by 2 cos theta is plus or minus 1. So you will get pi by 2 cos theta is equal to, you will get 0 and 180 degree. Okay, 0 and 180 degree. When we rearrange, you will get cos theta is equal to 0 is only valid. What is the reason? If we consider 180, that is a pi, you will get, when we rearrange, cos theta become 2. Cos theta is equal to 2. It is not a valid case. So it is not possible. So we consider 0 only. So solve this equation, you will get theta is equal to 90 and 270. We get the maximum value at the angle 90 and 270. So here theta is equal to 90 and 270, you will get a maximum value. Then next we want to find the null points. Null means electric field intensity is 0. So here normalized electric field intensity is 0. We know that equation of normalized electric field intensity, that is cos pi by 2 cos theta, that is equal to 0. Then rearrange the equation, you will get theta is equal to 0 and 180 degree. In those points you will get nulls. Then half power points. Half power points means normalized electric field intensity is 1 by root 2 of its maximum value. We know that normalized electric field intensity is a cosine term. Cosine have maximum is 1. So 1 by root 2 into 1, that is 1 by root 2. We know that En is equal to cos pi by 2 cos theta equal to 1 by root 2. Here we consider plus or minus 1 by root 2. Rearrange the equation, you will get theta is equal to 60, 120, 240 and 300. In 4 angles, you will get half power. So we can plot the radiation pattern like this. we get a maximum at 90 and 270. So maximum is plus or minus 1. So plus 1 at 90 and minus 1 at 270. So here the starting from here, this is a 0, a 90, 180 and 270. And 90 and 270 you will get the maximum, and null points occur at 0 and 180. At 0 and 180 you will get electric field intensity 0 electric field intensity. And half power points occur at the angle 60 degree, 120 degree, 240 and 300. So this is the half power points. And this radiation pattern is termed as broadside radiation pattern. Okay, that's all. Thank you.